Data skew is one of the most painful Spark performance problems because the job looks almost finished, but it keeps waiting. In simple words, data skew means the work is not distributed evenly across partitions. Most executors may finish quickly, but one executor receives a much larger partition and keeps running for a long time. That single overloaded task can delay the entire stage. In this video, we will explain what data skew is, why one executor works harder than the others, how skew creates slow tasks, and how to identify skew in Spark UI. We will also cover practical fixes like salting, broadcast joins, better partitioning, and adaptive query execution. Skew is not random slowness. It is uneven work distribution. Data skew happens when one or a few partitions contain much more data than the rest. In a balanced dataset, partitions are similar in size, so tasks finish at roughly similar times. But in a skewed dataset, most partitions are light while one partition is very heavy. A common example is a hotkey. Imagine a customer ID that appears 120,000 times, while most other customer IDs appear only around 1,000 times. When Spark groups, joins, or aggregates by that key, all those records may be sent to the same partition. That partition becomes heavy and performance suffers. Skew starts in the data, then shows up in performance. Spark schedules tasks by partition. If most partitions are small, most tasks finish quickly. But if one partition is huge, the task processing that partition becomes huge too. That task may land on one executor, and that executor stays busy while the rest of the cluster has already finished its work. This creates poor parallelism. Instead of all executors sharing the workload evenly, one executor does most of the work while others wait. The result is long stage duration, lower cluster efficiency, and higher cost. This is why adding more workers does not always fix skew. If the data is still concentrated in one partition, Spark may still wait for one overloaded task. Skew creates slow tasks because a stage can only finish when its slowest task finishes. Most tasks may finish early, and the stage progress may reach 99%. But one oversized task keeps running. That single task can dominate the entire stage time. In Spark UI, this often looks like a long tail in task duration. You may see 99 tasks complete quickly, but task 100 takes much longer because it is processing a skewed partition. This is why skew can make a job feel stuck. The cluster is not completely frozen. It is simply waiting for the slowest task to finish. A single skewed task can dominate the entire stage time. To identify skew, use Spark UI metrics instead of guessing. Start by finding the slowest stage. Then sort tasks by duration and look for a long tail. If most tasks finish in a few seconds, but a few tasks take much longer, that is a strong skew signal. Next, compare input size, shuffle read size, spill, and executor activity. A skewed task often reads much more data, spills more to disk, or keeps one executor busy while others are idle. Common red flags include long tail tasks, one task much slower than the rest, uneven shuffle read across tasks, high spill in only a few tasks, and a stage that seems almost done but keeps waiting. In Spark UI, skew usually appears as imbalance, not just high averages. Salting is a technique used to break one overloaded key into smaller buckets. Imagine key A, or customer 101, appears too many times. Without salting, all records for that key may go to one partition, creating a very heavy task. With salting, we add a small random value or suffix to the key. Instead of one key called A, Spark now sees A1, A2, A3, and A4. This spreads the workload across multiple partitions and multiple tasks. For aggregations, you may aggregate first by salted key, then combine the results back to the original key. For joins, you may need to salt one side and expand the other side carefully. Salting is best for extremely hot keys in joins or aggregations. Salting spreads one hot key across many tasks. Broadcast joins can reduce skew pain when one side of the join is small. In a normal shuffle join, Spark may move data from both tables across the cluster. If the join key is skewed, one partition can become very large, creating a slow task. But with a broadcast join, Spark sends the small table to every executor. Then each executor can join its local part of the large table with the broadcasted small table. This avoids a large shuffle on the small side and can reduce the impact of skew during joins. Broadcast joins work well when one table is small enough to fit safely in executor memory. But they are not suitable when the broadcast side is too large. A broadcast join can avoid the shuffle that makes skew worse. Better partitioning helps reduce imbalance by spreading work more evenly across the cluster. Poor partitioning creates uneven partitions. Some tasks are tiny, while one task does most of the work. Better partitioning creates more balanced partitions, which usually means more even task duration, better resource usage, and faster stages. The key is to choose partition columns carefully. Use keys with better data distribution. Avoid very high cardinality keys that create too many tiny partitions, and avoid keys where one value dominates the data. Filter early before repartitioning, so Spark moves less unnecessary data. Also remember the difference between repartition and coalesce. Repartition can rebalance data, but usually triggers a full shuffle. Coalesce can reduce partitions with less movement, but it may not rebalance data well. Partition quality directly affects skew, parallelism, and stage time. Adaptive query execution, also called AQE, allows Spark to adjust the physical plan during runtime. Before AQE, Spark starts with a plan based on estimates. But at runtime, Spark can observe the real size of the data and adjust the plan. For skew handling, AQE can help split skewed partitions and rebalance some join work. It can also coalesce small partitions to reduce overhead, and in some cases, change join strategy when real data sizes make another plan better. This matters because skew is often easier to see at runtime than before execution. AQE is powerful, but it does not replace good data design. You should still understand your keys, partitioning, joins, and data distribution. AQE can reduce skew pain by adapting the physical plan at runtime. Let us recap the data skew diagnostic workflow. First, identify the slow stage in Spark UI. Second, inspect task duration and partition imbalance. Look for tasks that are much slower than the rest. Third, review shuffle, read, and spill. High shuffle or disk spill in only a few tasks is a strong imbalance signal. Fourth, find the hotkey or skew source. Analyze key frequency and understand which value or pattern is overloading the job. Fifth, apply the right fix. Use salting, broadcast joins, better partitioning, or adaptive query execution depending on the root cause. Finally, validate the result. You want lower stage time, more balanced tasks, less spill, and lower shuffle read. Skew is an imbalance problem. Diagnose the data pattern, then choose the right fix.